Hello, my name is Valentin Voroshilov. I've been teaching physics at different places, mostly at Bridgewater State and at Boston University. And I've been doing this for a long time, and I consider myself to be good at doing that. Unfortunately, I can't present this lecture face-to-face to you. That's why I make this video. However, I'll see you soon next week on Tuesday, according to our general schedule. So our materials will be available on Blackboard. The syllabus, homework assignments, the lecture notes, all materials will be there. So please check if you have the access. And if you don't have the access to Blackboard, please let me know. And our textbook is free for download from this link. And a copy of a textbook should be available through Blackboard. Maybe not the latest copy. They make slight modifications every year, but they're all the same, basically. So if you check the syllabus, and you should, you can see our schedule, what topic will we talk about, and what labs. The lab schedule might change a little because Professor Hernandez is responsible for running labs, but he will tell me if any change happens, and I will inform you, or he will inform you directly. And the syllabus also tells you in general how the final grade will be calculated. It's based on your lab grade, homework grade, and participation grade. And for participation grade, all you have to be is just be here and participate. And the lab grade is calculated by Professor Hernandez. And the homework grade is based on the homework. The homework 1 is already available on Blackboard. You should print it out and bring it back to me when it says due to. And this is a generic Bridgewater State grading scale. Usually I don't make any changes unless something really drastic happens with the distribution. And in the end, we can calculate the total grade using this equation. It's based on 2 midterm exams, final exam, lab grade, and the homework and participation. There's a common misconception, I would say, a myth, that physics is really hard. I don't think physics is hard. First of all, there are much harder things in life than physics. For example, learning how to balance on a rope is much harder for many people than learning how to solve a problem about person balanced on the rope and calculating all the forces. We will do something like that later. So physics is not really hard if you follow the logic. And physics has logic. Physics is applied mathematics. We have to use some mathematics, but we don't have to use any calculus. Simple algebra and the trigonometry is sufficient. And we study physics because we want to use the knowledge to make our life better. Eventually, we have to use our knowledge to make reliable predictions. And if we can make reliable predictions, we can build things which are convenient for us, like a projector, a car, or airplane. Every science has a mission of making reliable predictions. That's it. That's what science is for. That's what science is about. And when we look around to make a prediction, we search for things which repeat themselves. We call them patterns. If we observe a pattern, that pattern tells us how to make a prediction. For example, every morning we observe the sun rising and then coming down. So we observe it again and again, and we can make a prediction. It's going to happen tomorrow, the day after tomorrow, the day after tomorrow, etc., etc. And there are many different patterns in nature. Yeah. Procedural patterns, visual patterns, logical patterns, and audio patterns, social patterns. Of course, for us, most important patterns are numerical. Like this is a famous Fibonacci sequence, 1, 1, 2, 3, 5, and we can see the pattern. If we see the pattern, we can predict what should be the next number in this sequence. And we don't really think about it. We just know it. We know that to find the next number, we have to add 2 previous numbers, because that's what our brain tells us. 1 plus 1, 2, 1 plus 2, 3, 2 plus 3, 5, 3 plus 5, 8, etc., etc., 13 plus 21, 34, etc., etc. And our brain is a very powerful pattern recognition machine. If it wasn't be for our brain, we wouldn't be able to do science. In physics, we have special patterns. Some we call definitions. Yeah. We define this to be equal to that. Like the easiest definition is speed. Speed is distance divided by time. Well, technically, it's average speed. And a definition depends on common agreement between people. Someone offers a definition, and if it works for everybody, everybody agrees eventually to use it. Laws don't depend on agreement. We study nature, we search for pattern, and that pattern eventually is described mathematically in the form of some equation, and that equation is a law. And of course, we use some mathematical procedure, not really physical laws, but handy part of knowledge, equations, functions, graphs. When we study any phenomenon, we start from observations. So this is a standard free fall situation. I release a ball from rest, and it falls. We do it again and again and again until our brain sees the pattern. And the pattern is, if we take a cell phone or a camera and tape the motion of this object and then look at it every second or every half of a second, we can see that distance changes in a certain way. We can take a ruler and measure distance as a function of time. We can put those numbers in a table. Then we can graph how position changes in time. And eventually, we can derive an equation which represents this relationship. And if we have that equation, now we can make a reliable prediction. We can ask, for example, what would be y number equal to when time equals, I don't know, 0.736. So all we have to do is plug in time, take a calculator, and calculate. And speaking about a calculator, any calculator with the standard trig functions will do. So this is a summary. Physics is a science, and every science is based on a vast amount of data. We have to analyze those data, arrange them. Not everything which is called science is actually a science. For example, physics is science. Teaching physics is not. There isn't reliable data which would help us to make a prediction, for example, who's going to get a certain grade in the end. It's just impossible. So when we observe things in physics, when we see something important, we give it a name, like that's what we call a distance, that's what we call time, that's what we call speed. Mathematical definition usually helps us to relate some of those names. We call them also variables, the physical quantities. And in order to assign a number to any of those physical quantities, we have to use a specific procedure. That procedure has a name, a measurement. If you Google measurement, you can see something like this. There is a science called metrology. That's what they call measurement and metrology. It's not very good for us. It's not very specific for physicists because it doesn't specify a procedure. In physics, this is what we call a measurement. If we want to measure certain quantity, first, we have to set a standard of that quantity. Second, we have to set a procedure which would allow us to compare all other objects which have the same quantity with the standard. And in physics, we have several important standards. Number one is time. To measure time, first of all, we need a periodic motion, something like this, a motion which repeats itself. 1 Mississippi, 2 Mississippi. So now we can call this time interval 1 second, for example. And now we can count how much time, how much seconds, how much motions like this is fit in any time interval. Of course, we don't do it anymore. Well, we can use a kitchen timer or a clock to measure time much more accurately than using this ball and a string. And if we use a special set of measurements, we call them units, physicists and engineers and scientists in the whole world agreed on using the same set of units, the same set of standards. So there is a special system called International System of Units, or SI. So if we measure time using the International System of Units, we have to use seconds. But of course, in everyday life, we also can use minutes, hours, days, months, years. It's up to us. But when calculating anything related to time, we have to use seconds. Second standard is the standard of length. And the standard of length has been changing historically. The easiest and the most common standard is just a rod chosen to be equal to 1. 1 what? Well, the rod like that was called 1 meter. It was divided into smaller parts, decimeters, centimeters. And if now we want to measure the length of something, we just have to count how many of these standards can we fit. For example, if I want to measure the length of this bench, I just have to count 1, 2, 3. I fit it 3 times exactly, so the length of this bench is exactly 3 meters. And the next standard is the standard of mass. So to measure mass, we could use our own feelings, right? Okay, well, probably, yeah, I feel like it's maybe 1 kilogram. But we people are not very good at accurately measuring things. So that's why we have invented scales, a spring scale or an electronic scale, which is a graduated device. So I place a standard which I call 1 kilogram. I write number 1, and then I can calibrate. It's smaller parts, 10th, 100th grams, milligrams. And now any other physical quantity can be described in terms of seconds, meters, or kilograms. This is a standard exercise when we need to make a conversion from one set of units into another set of units. Here, we need to convert 54 miles per hour, which is not a unit of International System of Units. into meters per second, which is a unit of international system of units. So to do that, we have to use so-called conversion factors. And conversion factors are openly available in a textbook online. And we know some, for example, 1 hour is equal to 3,600 seconds. We know that. 1 day equals 24 hours. 1 metric ton equals 1,000 kilograms, et cetera, et cetera. Here we need to make two conversions, from miles to meters and from hours to seconds. So we'll literally make a search for a conversion factor which relates miles and meters and hour and seconds. So 1 mile is equal to 1,600 meters. 1 hour is equal to 3,600 seconds. So now we can use these factors to make a conversion. What do we do? Well, the number with the unit represents a product of a number and algebraical type variables. So we don't touch the number. We rewrite the units given to us as a fraction. And then we do mathematical operation which has a name, a substitution. Because 1 mile is the same as 1,600 meters. We can replace 1 mile with 1,600 meters. Because 1 hour is the same as 3,600 seconds. We can replace 1 hour with 3,600 seconds. So now we can simplify. Well, we can take calculator and calculate it. And what is going to be 54? 54 is 9 times 6. 36 is 6 times 6. And that's 16. Yeah. So 6 and 6. Now 3, 2, 8, 24 meters per second. This is a very common example, and now anytime when you need to convert some unit into another unit, you know what to do. You have to search for a conversion factor and you have to apply it. This is a possible conversion factor, not all of them, of course, but if you're not sure, you always can find it online. Now, we're going to talk about mechanical motion. What is motion? How to describe the motion? Well, we start from this question. So you don't see me, but you see this page, and you see these two objects and one silver, yellow, red, silver. And I'm going to perform an experiment. Please watch closely. That's an experiment. And now the question is, was this object, the yellow one, moving? And if the conversation goes back and forth, some people say yes, some people say no, but unless we say relative to what we're considering the motion of this object, we actually can't say anything. Because if we look at these two objects, they don't move relative to each other. What does it mean? It means, for example, if you use our imagination, we are sitting here and we're watching at the yellow object. Relative to us, it remains at rest. We're watching, same distance. But, of course, relative to the silver object, so if we use our imagination and pretend we are here watching the same yellow object, of course, relative to us, the object is moving. So this simple experiment tells us that the motion is relative, and it's very important to keep in mind when we talk about the motion, when we try to describe the motion, keep in mind relative to what? And most of the time, it is assumed that the motion is being considered relative to the ground, relative to a tree on the ground, relative to a bush on the ground, relative to a person standing on the ground. Now, we need to introduce special physical quantities which would help us to describe the motion more accurately. Well, let's say we need to travel from the initial location to the final location using this path. First of all, it always takes some time. Yeah, and that time has a name, elapsed time, or just time to travel, or just time, people call, from initial to final. And of course, we traveled a certain distance. The line which represents our path has a name, trajectory. And an official definition of distance is the length of the trajectory. So how would we measure this length? Well, we can count these blocks: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the length of this trajectory, 13 blocks. A block is a unit of length. If we knew a conversion factor, for example, 1 block equals 100 meters, we could convert length from blocks to meters. But that's not the only way to describe our motion. What if we really don't care how did we get from point to point? All we care is where we were and where we're now. In that case, we can use a different variable. We call it a displacement. And this word displacement kind of tricky. First, it describes, does the action an object is being displaced, we displace it from here to here. Now, very often, it only describes the distance, direct distance from the initial point to the final point. People also call it a displacement. But an actual definition of a displacement is an arrow which connects the initial point and the final point. So it has an arrowhead, it has a direction. And the displacement in the first sense is equal to the length of the magnitude of the absolute value of that arrow. And it's very important to know this language, because if we need to calculate displacement, we need to know what it means. When we need to calculate distance, we need to know what it means. So distance, 13 blocks. Displacement, an arrow. And you probably know that in mathematics, people call an arrow a vector. So we also can call it a vector, which points from the initial location to the final location. That's it. But also, again, people sometimes use the same word displacement for the length, for the magnitude of this arrow. Same word. Well, let's use this problem to practice with this material. Every time when we have to solve a problem, first we have to draw a picture. We have to visualize what's happening. And for that, we have to use our imagination. So a person walks 4 meters west. So west means to the right, to the left. 1, 2, 3, 4. 4 meters. That's the displacement, but not the whole, not the total, only the first part of it. Because after that, the same person makes a turn and travels down. And that displacement has a length of 3 meters. And the question is, what is the total distance traveled? Well, we know, but according to the definition, total distance traveled is supposed to be equal to the length of the trajectory. This is the trajectory, and we can see that the trajectory will be equal to, the length of the trajectory will be equal to 4 plus 3, 7 meters. You just follow the definition. 7. Of course, natural question now, what was displacement? And of course, we have to repeat the same picture. We start here. We walk 4 meters west. We make a turn. We walk 3 meters south. Now we are looking for the displacement. But we cannot find the variable which we don't see. So we have to follow the definition of a displacement, and we have to draw that arrow which represents it. That's the initial location of an object, well, of a person. That's the final location. And this arrow represents the displacement. Now we need to calculate the magnitude. The magnitude is the length of this side of this triangle, which has 2 known sides. And it's not some kind of a general triangle, not obtuse, not acute. This is a very special triangle. It has a 90 degrees angle in it. How do we know? Because we know that this is the angle between the directions west and south. So, if it's a right triangle, we can apply the Pythagorean theorem. So the Pythagorean theorem immediately tells us that s squared should be equal to 3 squared plus 4 squared, or we can solve it. And that will give us 5 meters. So this is actually a standard 3, 4, 5 triangle. And we will be using similar trigonometry in the future many times. That's why we need to refresh what we know about right triangles. So of course we know the Pythagorean theorem, but also we know how to calculate different functions related to the angles of a triangle. For example, if I want to calculate the sine of this angle, I have to divide 2 numbers. One number represents the length of the side opposite to the angle, and second number should represent the longest side of a triangle, which we also call hypotenuse. And cosine and tangent. We will be using these equations very often. So you can maybe even make a copy of this page in your notebook or print it out and keep it with you. Well, this completes our first lecture. Thank you very much, and I'll see you very soon. Bye.